Okay, so this is going to be an overview of section 10.1. We talked about Avogadro's number in our introduction to the mole, and now we're going to talk about why it's that number. How the heck did that number come to be? Okay, so we remember, so skip down in section 10.1 in your notes packet to the what is a mole section. And remember, the definition of a mole is 6.02 times 10 to the 23rd. Representative particles of a substance, but really anything. The word mole means that number of things, Avogadro's number. So Avogadro's number, we're going to talk about that number now and do a little bit of class notes. The value, again, you can just write 6.02 times 10 to the 23rd. And I want to do a math proof of the value before we do the why this number section in the notes packet, okay? So the math proof, here's the deal. When Amedeo Avogadro was working with chemistry, okay, all atoms, all elements had been assigned an atomic mass, okay? So for example, if we look at our periodic table and we look at carbon, 12.0 is the average atomic mass of carbon, which means that the atoms of carbon weigh 12 AMUs, okay? So remember that those numbers so far have been representing AMUs, atomic mass units. Well, the problem is we don't have scales that can measure atomic mass units because atoms are incredibly tiny. An atomic mass unit is very, very, very small. But it had been defined as a specific number of grams back in the days of Amedeo Avogadro, okay? So this is the definition of an AMU. 1 AMU, let me see, make sure I don't go too high here. 1 AMU equaled, by definition, 1.661 times 10, 1.661 times 10 to the negative 24th grams. Okay, super, super tiny, like way too small for us to even comprehend. So one of the goals of Amedeo was to figure out, well, how can we make these mass numbers in the periodic table have more meaning? Well, we could put them into grams, and instead of grams of a single atom, because that would be a really, really tiny number, we can make them grams of a mole. So he created the concept of a mole and make those grams equal the AMUs of the atom. Okay, so we're trying to give that number two meanings. Okay, so here's an example of what he focused on. He was thinking, so for the math proof, this is what we would want to write. Okay, he was thinking, how many atoms of carbon, how many atoms of carbon would we need to get 12.0 grams of carbon? Okay, now why 12.0? Well, I just pointed out that carbon's atomic mass on the periodic table is 12.0 AMUs. Okay, so how many atoms of carbon would we need to get 12.0 grams? The same number of grams that the single atom would weigh in AMU. So give that number double meaning, okay? So what we start with is we start with that 12 grams. That's the number in our question, okay? So we start with 12.0 grams of carbon, okay? And we're trying to figure out how many atoms that is. So we set up a conversion factor label method, and we know that grams and AMUs have this relationship, okay? So I'm going to put grams on the bottom to cancel, and I'm going to put 1 AMU on the top. 1 AMU equals 1.661 times 10 to the negative 24th grams, okay? So the grams piece cancels out, okay? 1 AMU equals 1.661 times 10 to the negative 24th grams. Now we also know that an atom of carbon weighs 12.0 AMUs. So if I want the AMUs to cancel, I'm going to put 12.0 AMUs. On the bottom is 1 atom for this element. okay? So AMUs cancel out. When we punch this into the calculator, we end up with Avogadro's number, 6.02 times 10 to the 23rd atoms. And that is how he came up with the number for the mole, okay? I'm not going to ask you to reproduce this proof anywhere, but when you have a definition of AMUs to grams and you want that mass number, that 12 AMUs, to have double meaning, that's how you connect the two. If you have this many atoms of carbon, it's going to weigh the same number of grams as a single atom of carbon weighs in AMUs. If you have this many atoms of nitrogen, it's going to weigh the same number of grams as a single atom of nitrogen weighs in AMUs. Any element, it will work, because if you look at the grams and the AMUs, those two numbers cancel. And if you choose a different element, those two numbers would still match. You're choosing to make that mass number represent two things, okay? So why this number? Why this number? I'm going to go ahead and just point this down so you can see what I'm going to write here. Why this number? This gives the mass number in the periodic table double meaning. This gives the mass number in the periodic table double meaning. The mass of one atom in AMUs, the mass of one atom in AMUs, and the mass of one mole of atoms in grams. And the mass of one mole of atoms in grams. All right, so there we go. Every number in the periodic table, every mass number, excuse me, has two meanings, okay? So pick an element, any element. If you look at nickel, 58.7 AMUs is the average mass of an atom of nickel. 58.7 grams is what one mole of nickel atoms would weigh. So all of these numbers now have double meaning, and it brings it to a value that we can work with. We can measure grams, we can't measure AMUs, but so now we can work at a larger number of atoms that we can actually quantify and use in the lab, okay? Okay, I want to go through the answers for the sample problems and lesson checks, so I'm just gonna read them off to you, okay? Remember, if you haven't figured this out yet, all of the sample problems are in the back of the book, and they have every step shown. So the mathematical steps are shown for the sample problems, and you can find your mistakes there. The lesson check problems do not have that, but I will give you those answers, and if you need me to talk you through or send you a picture of some work to show you how I got to those answers, please let me know, okay? So sample problem 1, the answer is 5.0 kilograms. Sample problem 2, in your calculator, you probably got 672 seeds, but for sig figs, we have to round it to 2 sig figs, so it should be 670 seeds. Sample problem number 3 is 4.65 moles of silicon. Number 4 is 0.360 moles of bromine. Number 5, 2.75 times 10 to the 24th atoms. Now on that one, if you got, hang on a second, let me figure out what this would be. If you got 6.88 times 10 to the 23rd, you're doing the problem right. But when you go from moles of SO3 to molecules of SO3, that's the number you get, 6.88 times 10 to the 23rd. But then the problem asks you how many atoms there are, and every molecule of SO3 has 4 atoms, an S and 3 oxygens. So all that together, we have to multiply your answer by 4, and that's where the 2.75 times 10 to the 24th comes from. Number 6, very similar, okay, very similar. The answer would be 3.83 times 10 to the 24th atoms of carbon and 1.02 times 10 to the 25th atoms of hydrogen. Again, you can look in the back of the book to see the work for those problems. Interpreting data on page 312. Part A is 600 AMUs and 50 AMUs. Part B is 12 to 1 because it will always be a 12 to 1 ratio from carbon to hydrogen. And then part C, when you have 36.0 kilograms of carbon and 3.0 kilograms of hydrogen, that is still a 12 to 1 ratio. So the number of atoms of each is still the same. Okay. Number 7 is 137.5 grams per mole. When you're doing number 7 and number 8, you're adding up the pieces of that molecule. So like we said, this number on the periodic table has double meaning. So for phosphorus right here, that 31.0 is going to be 1 mole of phosphorus atoms. And then we need PCl3. So we also need 3 moles of chlorine, which is 35.5, okay? So 3 times 35.5 for the chlorine, add that to 31.0, and you end up with 137.5 grams, which is 1 mole of PCl3. So you can say grams per mole, or you can say 137.5 grams equals 1 mole of PCl3. Number 8 is 84.0 grams per mole. Again, you're adding up all the pieces of that compound. Number 10, we use the mole to get those relationships. Number 11, the element molar mass is on the periodic table. Compound molar mass, we just add up all the elements. Number 12 would be 0.10 bushels. Number 13 is 0.249 moles. 14, with only 3 sig figs allowed, is 5.27 times 10 to the 24th atoms. And remember, at the end, each molecule had 5 atoms. So if you just used Avogadro's number to make a conversion, you're partway there. We also just need to multiply it by 5 because each molecule has 5 atoms. And number 15 is 136.2 grams per mole. Hopefully you guys did all right. Let me know if you need any help on any of those things.